our journey. It's almost over in chapter 2. We're about there. A couple more things, and I got to babble on a little bit about the absolute value of x. It's going to lead into stuff, and it's going to talk to us about where you can take a derivative. This word differentiable is basically like, where can you take a derivative? So differentiable at a point, typically. All right, whatever. There's words. Here is our question. Where is the absolute value of x differentiable? Now, there's a whole frickin' proof that goes into this thing, and typically we're in class, I'd do it, but it's in your textbook. You can go and look this thing up. So I'm going to draw the function, and I'm going to draw its derivative. We're just going to use logic here. There's a whole proof that goes into it with limits and stuff. Now remember, derivatives are limits. All right, there's limits inside of a derivative. Maybe I'm saying that wrong, but limits are part of derivatives. So let's draw the absolute value of x. Let's put that thing in. It's just two straight lines, right? F of x equals the absolute value of x. Dope, we got it. Your x's, your y's, right? So it's any point, so if you got 1, it's got to be 1, right? All that stuff. If it's -1, that's got to be +1. We got that shit. We know what's up. Cool. So now let's go find f prime. And let's just use logic to look at it. F prime of x. So what's the slope of this line right here? Or maybe it's easier to look at the slope of this line, because they're two different slopes. Maybe we look at the one on the right. What's the slope here? When we're to the right of x equals 0, what's that slope? It's 1. Look, it's 1. 1, 1. The slope's freaking 1. So we're saying if you ever have an x value that's bigger... Wait a second, I swear I've seen this before somewhere. So the slope is... actually, let me change the color on this. The slope is 1. No matter what. No matter what x value. Plug in 2, you're up at 2. Look at that. Your rise over run. Your change in x. Your change in y. They're both equal to frickin' 1. 1 over 1 is 1. Sweet. Let's look the other direction. Over here. The slope's negative frickin' 1. So whenever you have an x value that's less than 0, it goes this direction. There's our derivative. That's just the frickin' derivative. It's weird. It's like we've seen that somewhere before. Yeah, we take that out for some sort of reason. So we can look and say, well, shit, if there's a number here, that means that all of this derivative exists. This derivative exists. We're good everywhere as long as the limits work. So let's look. If we take a limit, let's go this way and let's go towards 0. Do our heights line up? Is this the same height as this height? Are those the same heights? No. No, they're not. At x equals 0, is not differentiable. So this function isn't differentiable. That means you can't take a derivative at 0. That's all it's saying. Everywhere else is all good. You can find the slope of that line anywhere, or those two lines. You can find these slopes anywhere. But down here, how do I draw the slope of my tangent line? Do I draw it like this? Or does it go like this? Or maybe it's flat? Which one is it? Because it's a sharp edge. And this is kind of how the game goes. And this one's kind of dope. All right, whether you follow this or not, catch this next piece. Well, maybe not that. We'll go back to that in a second. Here we go. 3 ways for f not to be differentiable. Sharp corners. Just like our absolute value of x had a sharp corner. We can't figure out what the slope is right up top here. I don't know what that is. I don't know whether it goes like this or like this or like this. I don't know how the slope of the tangent line is supposed to look. So no corners, cusps, or kinks. No corners, cusps, or kinks. You know, like a kink in the line, like this. That looks like a little, it's kinked. All right. Well, we wouldn't be differentiable at A because it's not freaking continuous. I'm going to take you back up and show you something. If f is differentiable at a, then f is continuous at a, which means if it's not continuous at a, then that implies that f is not differentiable. You can't take a derivative there. And it's just at one spot. So differentiable. Able to take a derivative. Well, we'll be back to that. We'll be back. So just for us when we're looking at stuff, if it's discontinuous there, how the hell are you supposed to find the slope of the tangent line? On what? What, just on this? Or up here? Which one is it supposed to be? Those limits don't exist there. The limit from the left and the limit from the right of this derivative, limit from the left and the limit from the right, they don't go to the same height. The other one is the vertical. If the slope is vertical, that means your slope has a slope of infinity or negative infinity. It doesn't. I'm totally lying. But it tends towards that as we have a vertical slope. We have it. So those things. No sharp corners, no cusps, no kinks. It's got to be continuous at that value. And no vertical frickin' tangent lines. That means that it's not differentiable there. You can't take a derivative at that point. But let's go back up to this. This is a theorem. It's a big one. If f is differentiable at a, then f is continuous at a. So what does this mean? If f is differentiable, then, if then, this is an if-then statement. If differentiable, that implies f is continuous. Oops, I should try and learn to spell even in shorthand. Is continuous. This does not imply the other direction. That little game I played with you was actually a game of logic of negation that I did before. But I'm not going to get into any depth on that. I'm just going to keep moving forward. Saying this is not a two-way street. Just because f is continuous does not imply that it's differentiable everywhere at a. Look, I'll show you an example. It's continuous at x equals 0. Okay? It's continuous, but it's not differentiable there because we got a sharp corner. All right? It's continuous, but it doesn't mean it's differentiable. It doesn't go back the other direction. Then red, that's bad. Only if it's differentiable, then we know for sure it has to be continuous there. So this was not a fun one. This wasn't a like, hey, how do you solve stuff? But it's going to help you to be able to read those graphs in 2.8, which are a pain in the butt throughout your homework, which are the majority of your freaking work. Also, I'm leaving out domains when doing this. As part of your problems, you're going to have to look at the domain of the function and the domain of the derivative. You got to look that shit up. You got to look that shit up. Domain is highly important. I've talked about it already at the beginning of the course, so it's up to you. All right, that's it for this one, and then we'll come back and I'm just going to show you the different types of notation so we can all speak the same language, and we're going to wrap up chapter 2. Hallelujah.